All right, so in science, right, if you want to know if something actually works, you have to compare it to something else. Simple enough. But what if the most powerful comparison was just looking in a mirror? Let's dive into that idea.
Not really. Just think about that for a second. In an experiment, instead of stacking your results up against a bunch of different people, what if we just compared you to you? How in the world would that even work?
You know, the standard playbook for an experiment is pretty straightforward. Group A gets the new drug. Group B gets the sugar pill. You see who does better. But we're looking at a totally different strategy here, one where the very same people go through every single part of the experiment.
Now, this whole idea has a name, and it's a real game changer in the world of research. It's called the repeated measures design. And yeah, it's all about one person experiencing all the conditions, which, as you're about to see, is where its real power comes from.
So in a repeated measures design, sometimes you'll hear it called a within subjects design, we're measuring the same person over and over, just under different circumstances. What this really means is that you get to be your own perfect baseline, your own control group. And this approach totally flips the script. Instead of wrestling with all the random differences between a bunch of people, one's a morning person, the other didn't sleep well, we're just looking at the variation within a single individual. It makes for a much, much cleaner, more direct comparison.
And the advantages? Oh, they are huge. For one, you need way fewer people, which is a lifesaver if you're studying a rare disease or a very specific group. It's super efficient. But the biggest selling point is that it's more sensitive. It's kind of like using a high-precision microphone that can pick up the faintest whisper in a crowded room.
So what do I even mean by sensitive? Well, think about it like this. You are way more like yourself yesterday than you are like your neighbor, right? So by using you as your own control, we cancel out all that random noise that comes from comparing different people. And when all that static is gone, even really small, subtle effects from the experiment are much easier to spot.
Okay, so this sounds pretty perfect, doesn't it? A super-powered, elegant design. But, of course, there's a catch. There's always a catch. This beautiful design has a sneaky little flaw built right in, a problem that can totally distort your results if you're not careful.
And this flaw is what we call practice effects. It's a simple idea. Just by doing the same task over and over again, people change. And here's the kicker. Those changes have absolutely nothing to do with what the researcher is actually trying to test. It's the experience itself that's causing the change.
Now, sometimes this can be a good thing. Practice makes perfect. You do a memory test once, you do it a second time, and you get better. You learn the ropes, you get a little faster, a little more accurate.
But it can also go the other way. By the third or fourth time you do that same memory test, you might just be bored out of your skull. You get tired, your motivation drops, and your performance actually gets worse. So now we've got a big problem. The order in which you do these tasks matters a lot.
So what do you do about that? How do you keep all the amazing benefits of this design without falling into the practice effect trap? Well, researchers have a brilliant secret weapon they can use to fight back.
That weapon is called counterbalancing, and the logic is actually pretty simple and elegant. If the order of the tasks is the problem, well, then let's just shuffle the order. By strategically mixing up the sequence of conditions, those practice effects get spread out evenly so they don't pile up and unfairly help or hurt any single condition. Now, there isn't just one way to do this. Researchers basically have two main master plans for how to pull off this counterbalancing trick, and which one they choose really depends on the kind of experiment they're running.
Okay, Plan A is what we call the complete design. In this setup, every single person experiences every condition multiple times, but they get them in different shuffled orders each time. The whole goal is to balance out those practice effects within each individual. A classic example of this is something called AB-AB counterbalancing. And it's just what it sounds like. You do condition A, then B, then you flip it, and do B again, then A again. See what that does? It ensures that both conditions get a turn when you're fresh and have no practice, and when you're experienced and have lots of practice. For that one person, it all just averages out.
But what if you can't have people do the tasks over and over? Maybe it's just too long or too tiring. Well, that's when you bring out Plan B, the incomplete design. With this one, the balancing act doesn't happen for one person. It happens across the entire group of participants.
So with this design, each person experiences the conditions only once, but everyone gets a different order. You can see it here. Some people get A, then B, then C. Others get C, then B, then A, and every other possible combination is used.
What's the result? Across the entire group, condition A shows up in first, second, and third place an equal number of times. Same for B and C. The group's average isn't skewed.
Okay, so we had a problem. Practice effects. We found a solution. Counterbalancing. We're all good, right? Story's over? Well, not quite. There's one more monster lurking in the shadows, a more subtle and honestly a more dangerous problem that our hero, counterbalancing, can't always fix. And this monster is called differential transfer. This is what happens when one condition doesn't just fade away. It leaves a lasting mark that actually contaminates your performance in the next condition. This isn't just about being tired or unpracticed. It's a fundamental change caused by what you did before. The best analogy for this is the old "don't think of a pink elephant" trick. If the first task teaches you a new strategy or gives you some key insight, you can't just unlearn it for the second task. That knowledge is there now. The effect of the first condition literally bleeds into the next one. And when that happens, counterbalancing can't save you. It's useless. The only real solution is to abandon the repeated measures design completely. You just have to go back to the standard way of doing things, using different people in each group. And that's not a failure. Sometimes it's just the smartest call to make. So let's just quickly recap this whole journey. Repeated measures designs are incredibly powerful tools. They need fewer people and they're super sensitive. Their main weakness is the practice effect. The hero that comes to the rescue is counterbalancing, but the one villain it can't defeat is differential transfer. And knowing which problem you're facing and choosing the right design for the job, well, that's what good science is all about.
And that leaves us with one final thought. We've talked a lot about how practice, fatigue, and the order of things can completely shape the results of an experiment. So the next time you sit down to study or learn a new skill, just think about this. How is the order in which you're practicing affecting your own progress?